Hello, everyone. Thank you for being here. My name is Daniela Hurtado Lange, and I'm a fourth-year PhD student in operations research at Georgia Tech. Today, I'll be presenting my work on heavy traffic analysis of the generalized switch under multidimensional state-space collapse. So what's our motivation? Well, our motivations are queues, processes where we arrive and we have to wait in line before someone can help us. An example is a toll, like in this picture, or call centers, ride-sharing apps, delivery apps, or anything related to the cloud. And what we want to do is minimize delay. So how we do this? Well, we approach the problems from a stochastic processing networks point of view. So the systems I showed you before will be drawn like this. Here's the simplest stochastic processing network, a single server queue. Here's a single queue with multiple servers, or a parallel server system where we have a bunch of queues which might be correlated. Here's an example of how these queues may be correlated. For example, we might have a bunch of queues and we have control on the arrivals. So whenever there's an arrival, we decide to which queue to route it. Or maybe the control is on the service. Maybe the servers are correlated and we need to decide how to process the jobs. Or even more generally, we can have a network of queues. So after our customer leaves one queue, they may join another queue before leaving the system. And the question is, again, how to understand delay in these systems. In this talk, I'll be focusing on systems that have control on the service process, not on the arrival process. So the outline for the rest of this talk is as follows. First, I'll present the generalized switch model, and I will show you what's the capacity region. Then I will jump into the main result. I will first define what is heavy traffic. I will present the statement and some examples that will help us interpret the result. And at the end, I will present a proof sketch and then conclusions. So let's start with the model. In order to present what's the generalized switch, I will start with an input queued switch, which is an ideal model for a data center network. So an input queued switch is a discrete time system where the number of queues is a perfect square. There are L input ports and L output ports, and each input-output pair has a different queue. Each queue has a different arrival process that might be correlated or not with each other. And the service occurs at the outputs. Every packet that arrives has the same size, which is equal to 1. And in each time slot, we can serve at most one queue from each input and from each output. Then we need to solve a scheduling problem in order to decide the potential service vector. The capacity region of this model is this set C right here. And it says that in each row and in each column of this system, the arrival rate has to be less than or equal to 1. Why 1? Because we can serve at most one packet from each row and each column in each time slot. So a different way to write this capacity region is as follows. So notice that since all packets have size 1, then the potential service vector is a permutation matrix. So let's call capital S the set of permutation matrices. Then the capacity region C can be also written as the convex hull of this set capital S. Keep this in mind because it will be important for the capacity region of the generalized switch. So now, how we generalize this system? Now, instead of having a perfect square number of queues, we have any number of queues. And each queue, as before, has its own arrival process, and the service process will be denoted by S. So in the input queued switch, we had specific constraints on the vector of service. But in the generalized switch, we will just know there is some set of interfering constraints. And also in the input queue switch, these constraints were constant. So in every time slot, we see the same set of physical constraints. However, in the generalized switch, there are external conditions that affect our constraints. And we will call these conditions channel state. We will assume that this channel state is IID across time. And we will denote by M the possible channel states. So if channel state is small m, then the feasible service rate vector will be S super m. So examples, if we fix the channel state, of course we have the input queue switch, or maybe another example, which is not so obvious, is another wireless network. If we assume that the channel state changes with time, we can add fading to this ad hoc wireless network, or we can also have a parallel server system. Now, what's the capacity region of the generalized switch? So we will call psi m the PMF of the channel state. And then the capacity region is this set right here. So it's the weighted sum of the convex hull of the sets of feasible service rates in each channel state, and the weights of the sum are the probability of occurrence of each channel. Now, if we assume that the channel state has a finite state space and that each of these sets Sm is finite as well, then the capacity region is a polytope, and we will denote each of the facets by CL.x less than or equal to BL. So here in the picture, I highlighted 3 of the facets in 3D. Now, how are we going to solve the scaling problem? We will solve it using max weight, which means that we will maximize the weighted sum of Q lengths in each time slot, and we will pick the scale that maximizes the maximizer, sorry. Now, what's the weight? The weight will be the possible service rate vectors. So mathematically, if we already know the channel state is M, then we will pick the potential service rate vector that maximizes x dot q, where q is the vector of Q lengths and x can be any service rate vectors in the set Sm. We will assume that the arrivals occur before service, so the dynamics of the queues occur with this equation. So Q length in time slot k plus 1 will be the previous Q length plus arrivals minus potential service. And since this is potential service, we have to take the positive part because Q lengths cannot go negative. Or alternatively, instead of using the positive part, we can use unused service. Why would we like to add a variable that depends on everything else? Well, because it satisfies a nice condition. And it's that Qi in times dot k plus 1 times the new service in times dot k is always 0. Why? Because if there's a new service, then it means that potential service is larger than queues plus arrivals. So I could have served more packets than the ones that are available. And therefore, it means that if a new service is positive, then the queue length must be 0 in the next time slot. However, if I compare Q length in k plus 1 with a new service in k in different queues, then the product might not be 0. So now the main result. First, what is heavy traffic? Heavy traffic means that we load our system to its maximum capacity, where capacity is related to the capacity region. So for example, in a single server queue with arrival rate lambda and service rate mu, we know that the capacity region are all the values of lambda that are strictly less than mu. And then the heavy traffic limit is the limit as lambda goes to mu. So in general, if we have any capacity region, which is in this case a polyhedron in the picture, then we take a vector nu in the boundary, and in this work, we scale the arrival rate vector as 1 minus epsilon times mu, where epsilon is a number between 0 and 1. And the heavy traffic limit is the limit as epsilon goes to 0, which is one way to take the limit as lambda goes to nu. So this is the main theorem of our work. We compute the heavy traffic limit of a linear combination of the Q lengths, where the linear combination depends on the point at the boundary of the capacity region that we are approaching. Here I have two examples, one in a corner, one in the interior of a facet. And on the right-hand side, we have the linear combination of the correlation matrix of arrivals and a linear combination of the correlation metrics associated to the service process, which is, of course, related to the channel state. What linear combination? Well, this matrix C right here is related to the point nu that we are approaching in heavy traffic. So for example, in this example, this point nu is at the intersection of facet 1 and 2, and then the matrix C will have columns C1 and C2. In the second example right here, the matrix will be just C2. And in the linear combination of arrivals is governed by the projection matrix on the subspace where state space collapse occurs. And I will explain later what's this subspace. So now let's see what this means in terms of queuing systems that we know. In terms of the input queued switch, that, as you may remember, is this matrix kind of queuing system that models a data center network. On the left-hand side, we obtain the total queue length. And on the right-hand side, we have some linear combination of the variance of arrivals to each of the queues, plus its covariance with the same row and column, minus the covariance over the rest. And then we sum these overall queues. So for example, for the first term, 1, 1, I will have variance here, plus variance here, plus covariance here, minus covariance here. This is a generalization of a result proved in 2016, where it was obtained the heavy traffic limit of the total queue length for the independent arrivals case. However, in data center networks, independent arrivals is an unrealistic assumption. So this corollary is also of importance. Another example is a parallel server system. So consider a bunch of queues where the arrivals are correlated, the services are correlated, and we know the covariance metrics in both cases. So we, applying the theorem of our paper, we can obtain that the linear combination of queue lengths, which is governed by the service rates in each queue, is basically the sum of variance of arrivals plus variance of services. First observation is that we only have variances on the answer, not correlation, even though the arrivals are correlated. And if we have independent queues or correlated queues, the result is the same. And also if we have a single queue, this recovers Kingman's bound. Another interpretation is a generalization of the previous system. So consider a generalized switch and suppose that the state space collapses into an n-dimensional subspace. So for example, in this picture, we have a two-dimensional system and we're collapsing to this red cone right here, which even though is smaller than the whole space, it's still two-dimensional. So in this case, our result gives this quantity. And observe that on the right-hand side, we only have dependence on the variance of arrivals, not on the covariance between them. And as I said before, an example of such system is a parallel server system. Now let's jump into the proof sketch. So we use the drift method, which means that we first prove state space collapse. And we prove collapse to a set that we call K, sorry. And we will call Q parallel the projection of the vector of Q lengths on K. Then we set to 0 the drift of the right test function, which happens to be norm square of Q parallel. And then we do some algebra and we use properties of the system to obtain the heavy traffic limit. So what's state space collapse in this system? Let lambda be the arrival rate to each Q. And we will parameterize the system by the point nu that we're approaching in the capacity region in this manner. So we let lambda be 1 minus epsilon times nu, or epsilon is a parameter between 0 and 1. This system has been studied in the past under the complete resource pooling condition, which means that our system will behave as a single server queue in the heavy traffic limit. This happens when nu is at the interior of a facet of the capacity region. However, if nu is at a corner or at the intersection of more than 2 facets, then to the best of our knowledge, we're the first ones to study this system. And furthermore, our result involves both cases. So how do we prove state-space collapse? We will call P the set of indexes of the facets that intersect at nu. So in this example, the set P will be 1 and 2. And we will prove that the cone K generated by this C1 and C2 that determine these facets that intersect at nu is the subspace where state-space collapses. In other words, if we call Q parallel the projection of Q on K, and we call Q perp the error of approximating Q by Q parallel, then we can prove that the moments of the norm of Q perp are bounded. Therefore, as epsilon goes to 0, Q and Q parallel are very similar. Now, as I said before, we set to 0 the drift of this test function. If we do the algebra, we will obtain this expression right here, which has 4 terms. Term T3 is a new service, and intuitively, as epsilon goes to 0, traffic is higher, and therefore we shouldn't have a new service. So it's easy to prove that this term goes to 0. Then if you look at this term right here, it looks very similar to this expression that I showed you before. So using state-space collapse, we can also prove that T4 goes to 0. T1 yields the left-hand side, and T2 yields the right-hand side by solving the least squares problem. And this is how the projection matrix H appears. So now, do we know the expected number of packets in each queue in heavy traffic? Or do we know all linear combinations of the queue lengths in heavy traffic? The answer is no. If we take a linear combination that is equal to nu plus some vector in the direction of Q perp, then yes, we can have the result by state-space collapse. But if we have any other W, then we cannot obtain the heavy traffic limit using the technique I showed before with the drift method. So I just showed you the generalized switch model, which is one of the most general single hop queuing systems. And we developed heavy traffic analysis using the drift method. In particular, this equation right here is very important in our proof and same as state-space collapse. And future work is to obtain other linear combinations of the queue lengths, because with this technique, we can prove actually that it's not possible. I'll be happy to discuss why it's not possible offline. Thanks.